All right, now you're on.
All right, I'd like today to consider temperature, and we're going to be looking at the relationship between temperature and the structure of the atmosphere, and then we'll also fill in with a few important relationships for matter between specific and latent heat. And so first, let's just talk about temperature. Temperature we can think of as being a measure of the average of the square of the velocity, which is another way of saying that it's related to the average kinetic energy of the molecules in a substance. And if we're talking about a gas, these molecules are moving all over the place at very high speeds. Typically, the speed of the molecules in a room where the temperature, say, is 75 degrees, might be about 1,000 miles an hour. That's the typical speed of a molecule in this room right now where you're listening to this video. And so those molecules are really moving fast. And associated with that, we can measure the object's temperature. Now, there's also different kinds of molecular motions that are associated with solids and liquids. And we'll talk a little more about that later. But for the moment, let's just look at our basic definition of centigrade temperature. Here, this is based on the freezing and boiling points of water, so that we can say 0 degrees centigrade is a freezing point of water at 1 atmosphere's pressure, where 1 atmosphere's pressure is 14.7 pounds per square inch, as we discussed in a previous video. 100 degrees centigrade is the boiling point of water at 1 atmosphere's pressure. And degrees Fahrenheit has this kind of peculiar relationship to degrees centigrade. Even though we're used to degrees Fahrenheit, it typically is not used very often in a scientific context, just simply because it's not based on basic physical quantities, but rather it's based on the way in which Fahrenheit conveniently constructed its thermometer. But anyway, it caught on, and so this is the kind of temperature we use, and its mathematical relationship to our more useful temperature scale is that degrees Fahrenheit is equal to 9/5 times degrees centigrade plus 32. So we could show then that 212 Fahrenheit is the same as 100 degrees centigrade, which is the boiling point of water. At least at 1 atmosphere's pressure. This is going to change if we change pressure. If we go up, say, to the top of Mount Everest, at that height, the pressure might only be 1/3 of atmospheric pressure on the Earth. And it would boil much more quickly. And so if you were up there trying to boil an egg, all the water would turn to steam before the egg even heated up enough to cook it. And so you have to be careful if you're trying to cook things at high altitudes because of this differential in the freezing and the boiling points of water that is based on its pressure as well. But degrees Fahrenheit is 9/5 degrees centigrade plus 32, so that if we took, say, 100 degrees centigrade, plug it in, we get 9/5 times 100 plus 32. That's 180 plus 32 is 212. So that checks out. This allows us then to convert anytime we want from degrees Fahrenheit to degrees centigrade. 37 degrees centigrade is about 98.6 body temperature. 27 degrees centigrade is something like 80 degrees. So you kind of get used to these conversions if you use them often enough. One thing that we can say in general is, at least for a change in temperature, the change in degrees centigrade is about 1/2 what it would be for degrees Fahrenheit. Okay, and so if we had a change of 50 degrees centigrade, that would be more like a change of 100 degrees Fahrenheit. But not quite. You back off a little bit because there's a 9/5 factor, not a factor of 2 in front of degrees Fahrenheit. But it just gives you a basic idea of how the two are compared to each other. Now, temperature is of use to us in understanding some of the basic aspects of the weather. And we can talk about how warm different levels of the atmosphere are in terms of the amount of heat that can strike different parts of the atmosphere and be absorbed by different parts of the atmosphere. And so typically then, when we're looking at the properties of the atmosphere, we're often interested not only in pressure, which we talked about last time, but also in the temperature as well. And so let's keep that in mind. And what I wanted to do next is outline, if we go up to the top screen, the structure of the atmosphere. So the atmosphere starts out, it's got 4 distinct layers. We have the troposphere. This is where we live, right here. And this is up to about 10 kilometers in elevation, or about 6 miles. 10 kilometers is equal to about 6 miles. And so this is the height then of the troposphere. And it changes a little depending on where you are on the surface of the Earth and how hot the air is on the surface of the Earth at that point. But this is a typical height for the top of the troposphere. And so oftentimes our weather, we can see here, is confined to the troposphere. Notice here we have this unstable cloud, and it flattens out, and it can't get through that barrier to the next layer, which is called the stratosphere. Now, the reason for this barrier between the troposphere and the stratosphere, is what we call an inversion layer here. Now, what this means is that the temperature is going to start to increase in the stratosphere. And so typically then, as we go up to higher and higher elevations in the troposphere, we get a fairly, this is versus temperature we're looking at here, we get a fairly sharp drop off in the temperature. So it gets colder and colder the higher we get, until we get to the stratosphere, and then the temperature starts to increase. Okay, and so that's why we call this a temperature inversion layer leading to the stratosphere. So with the temperature dropping and then increasing like this, this creates a, not exactly an impenetrable zone, but one that is difficult to get through. And so commercial airliners typically tend to fly below this this inversion layer that connects the troposphere to the stratosphere, because it would be too hard to get through this layer. But what we have in the stratosphere down here are what are called ozone molecules. And that's the reason for the difference in the temperature. Because the ozone molecules absorb heat from the sun. And so these ozone molecules get hotter because they are more able to absorb heat from the sun. And so that means that as we get higher and higher in the stratosphere, we have these ozone molecules helping to heat the stratosphere. And so that means that unstable clouds from the troposphere, ones that kind of expand and rise, they tend to flatten out when they get to the top, and they can't get through this impenetrable barrier that is associated with the boundary between the troposphere and the stratosphere. So this distance here is about 10K, or 6 miles. And then the stratosphere goes up from about 10 kilometers to about 50 kilometers. Okay, so 50 kilometers, well, that would be 5 times 6. That would be about 30 miles up. So at the top of the stratosphere then, it would be at about 30 miles up, or 50 kilometers up, but the top of the troposphere would be at about 6 miles up. Now the tallest mountain on the Earth is at about, what, 30,000 feet, 29,000 feet? And so that then, if we take 5,000 feet per mile, then 6 times 5 is 30. So this is a little higher than Mount Everest. You know, maybe we're up at, instead of 30,000 feet, maybe 40,000 feet, something like that. That would be a typical value for the height of the troposphere. Then we go all the way up through this thinner zone of the atmosphere called the stratosphere. Go ahead and look back on the data projector. And then we have another boundary layer here. This boundary layer here is called the tropopause. This boundary layer here is called the stratopause. I'm just looking on page 13 in your textbook here. And then from there we go up into the mesosphere, where we get a temperature drop. So the temperature then rises in the stratosphere, but then associated with this stratopause, we have a temperature drop in the mesosphere until we get to about 80 kilometers. So we go from 10 to 50, and then from 50 kilometers to 80 in the mesosphere. And then everything above the mesosphere, looking back again on our picture, is this is called the thermosphere. And the thermosphere is everything above 80 kilometers high. And there's again a temperature increase in that region. Now the air is very thin up here, but it gets hotter. That the density of air is very low. So in other words, there aren't many air molecules. And so the thermosphere then is exposed directly to solar radiation. And so the temperature then goes up, but there aren't that many molecules to run into. So your definition for temperature isn't exactly what you would expect as being the same as your definition for how it would affect the human body, say, on the surface of the Earth. But interestingly enough, there have been people that have jumped out of airplanes from the thermosphere and fallen all the way through the mesosphere and then the stratosphere and the troposphere before pulling the ripcord on their parachute and landing safely. And one such person continued to accelerate because there's very little air resistance, because the air is so thin up here. And I had to breathe through an oxygen, source of oxygen, in order to keep from passing out. But it is estimated that this skydiver, real daredevil, broke the sound barrier. Went that fast and could have created a sonic boom, although the amount of air probably wouldn't have been enough to really hear a good solid shock wave. But what started to happen is this person started to tumble, and he wasn't able to use air resistance to adjust his rate of spin. So he started spinning faster and faster and faster and couldn't control it. And finally got before he passed out, he got down into lower elevation, was able to control his rate of spin, slow himself back down, and then was able to land safely. Okay? And so the properties of the atmosphere are such that he got more than he bargained for in that little skydiving adventure. But we can see that, just in summary here, that in the mesosphere, the temperature drops. And, and then in the stratosphere, the temperature increases. And in the troposphere, it drops. So if you go, say, up to the top of a mountain, and this is temperature here, then your temperature is going to get lower. Then it's going to go up in the stratosphere, it's going to drop in the mesosphere, or it's going to, drop in the mesosphere, and then increase again in the thermosphere. Okay, next thing I wanted to talk about is some of the properties of matter that we need to understand in order to fully describe what's going on with the weather. And so one of these is called specific heat. So this is a measure of how hard or easy it is to change the temperature of a substance. What kind of substance might I be talking about here? Well, typically, when we're using this in terms of our understanding of the weather, the substances might be, for example, land or water. Of course, we could be talking about this for any kind of metal would have a certain specific heat. A copper would have a different specific heat than aluminum, for example. Wood would have a certain specific heat. And so the way that we measure that is in terms of a quantity Q. We can think of this as being the amount of heat in calories that is necessary to change the mass of a substance by a certain amount. So we write it as Q equals mc delta T, where m is the mass of the substance, C is the specific heat, and delta T is the change in the temperature, which we just talked about in the last section. So what specific heat then is doing, basically, is controlling how much heat. Now this could, what would be the source of this heat? Well, it could be coming from the sun. That would be a very typical source of heat that we would be looking at in terms of meteorology. And then we would say, well, how easy is it for, say, water to change its temperature by means of absorbing heat from the sun? So what we would say then is that C for water is equal to 1 calorie per gram degree centigrade. So what that means then is that it takes 1 calorie of energy, form of heat, to raise 1 gram of water by 1 degree centigrade. Notice that this is in the centigrade units that I was talking about before. So this would be roughly 9/5 of that degrees Fahrenheit, or maybe 1.8 degrees Fahrenheit, if we were talking about Fahrenheit degrees. So that'd be the specific heat for water. the specific heat for land varies. It depends on the type of material that the surface of the Earth is made out of. And so it could be rock, or it could be different kinds of dirt. It could be mud. These would all have different values for the specific heat. But typically, the specific heat for land is about 1/5 of the specific heat for water, or 0.2 calories per gram degree centigrade. So what does this mean? It means that it's easier in terms of heat absorbed by the sun to raise land temperature than it is water temperature. So this, of course, is important when we're dealing with the heating of the Earth's surface. So what we could say then is that, just put simply, land heats up faster than water does under the influence of the sun. By heats up here, we mean increases its temperature. When exposed to solar radiation. And so typically then you could get an area, say like what we would have around here, have say Morro Bay. And then you go up over the coast ranges to Atascadero. And what we find is that the same amount of solar radiation coming in here as coming into the water creates more of a change in temperature over the land. And so this means then that particularly during the summer months, the land heats up more. And the water heats up less, even though it's absorbing the same amount of heat. So what this tends to do then during the summer is this creates a high pressure region, because higher temperature tends to produce higher pressure. Now, you can have low temperature high pressure zones too, but this is more normal, that a higher temperature will produce a higher pressure air mass. And then that higher pressure air mass is going to tend to rise. And so it'll experience a buoyant effect, just like a helium balloon starting to float away. And the high pressure region will rise up. And then that'll draw in air, because this is lower pressure. And so the lower pressure air will move in to try to fill in the void from the high pressure region. And we get what's called an onshore flow. And in California, we're quite familiar with this in terms of all the fog that starts coming in. Okay, and so that's a strong onshore flow. It's caused by a high pressure region basically floating up, creating a void, which then allows for the low pressure air to come in from the coast. And so that kind of cools things off a little bit and refreshes the inland areas. But if you get too far inland, then you no longer are in a position where you're going to get much cool air from the oceans. And so the really big deserts then tend to be farther inland, beyond the effect of the moderating influence of the ocean. Now, we also can have phase changes, and this is associated with different aspects of the weather as well. When we talk about a phase change, what we're referring to here is typically one of two different processes. We can either have solid to liquid. This would be considered a phase change. Or conversely, liquid to solid. Or we could have liquid to gas, or gas to liquid. And so when water boils, that would be an example of liquid to gas. Or in a more gentle sense, we could have water evaporation. So in other words, if the liquid, water, gets an appropriate amount of energy, it can turn into a gas. So this phase change then is driven by the absorption or release of energy. So this would be an example then of a liquid to gas phase change. Or we could have a gas to liquid phase change. But that would be condensation. This would tend to happen when the air cools and water droplets form. We could have a solid to liquid. Now, I mean, you could melt many substances. For example, you can melt a metal. And we think that on Venus, there may actually be melted metal rain that's coming down. But that's because the temperature is so hot. Typically on the Earth, the only kind of rain we get is water rain. And so here the kind of solid to liquid transition which is most applicable to what's going on the Earth would be ice to water. And a liquid to solid would then just be water freezing. Now, associated with all of these different kinds of phase changes, which either involve the absorption of heat when you go from solid to liquid or liquid to gas, or the release of heat when you go from liquid to solid or gas to liquid, we have what's called the latent heat. And that is the way of measuring how much energy is either absorbed or liberated by the water. And so associated then with this kind of a transition, we have what's called the latent heat of ice. That's equal to about 79 calories per gram. What does that mean? Well, and by the way, these aren't the kind of calories that you count. The kind of calories you count are kcals. Okay, so these are just 1,000 of those. But still, it's a certain amount of heat that is associated with 1 gram. Remember, there's 454 grams in a pound. So gram isn't much in terms of its weight. But here it takes 79 calories of heat to melt 1 gram of ice. Similarly, we have a latent heat for water. And this would be at 0 degrees centigrade that this would happen. Whereas the evaporation of water would happen at 100 degrees centigrade. So it already has to be this temperature before you can get this kind of a phase transition. Either 0 degrees for melting ice. So if it's not at 0, if it's like at -10, then you're not going to get the ice melting. And similarly, if it's not at 100 here, you're not going to get the water boiling. But once you reach that temperature, the latent heat for water is much more than the latent heat for ice. It's 540 calories per gram. And so the significance of that is similar to what the significance is here. It takes, in that case, 540 calories of heat to evaporate 1 gram of ice. That it works in reverse too. If you had, evaporate 1 gram of water. Whoops. So it takes 540 calories to evaporate 1 gram of water and turn into steam. Okay, so if you, let's say, had a bunch of water vapor and it were to condense into liquid water droplets, that could give off heat. So it turns out that kind of a process can happen inside of cyclones and hurricanes. And that is part of the energy flow that allows those systems to move and to grow. And so as we look at these different aspects of phases, I'll refer back to them, and we will see how they relate to each of the different meteorologic processes that we examine as we go through the semester.